we can somebody tell me like where we were at last time? I'm a little bit. I know like we talk about these things. 对啊，毕氏定理啊这些。然后 projection 开始有讲了吗？有讲了。OK， 那所以这个 section 结束了嘛，对不对？就是 section 1结束，那个是这边开始讲了吗？还是还没有？还没有。OK， 所以我们从那个没有讲嘛，也讲了。那讲到哪边？因为我有点那个，这个也讲了吗？这个 subspace 有讲了吗？也讲了。啊？没有。那所以上次是讲到这边吗？啊？没有 definition。OK， 所以 OK， 了解。OK， yeah。所以已经12月了。OK，it's already like last month. I believe 等一下，那个我们期末考试几月几号？25号。先跟你们确认一下，如果25号的话，今天是今天是4号，所以还有2次的课，就期末考了，是不是 ？OK， 好，那我今天那个 OK， 所以提醒大家一下 ，OK， 我们还有1次小考 ，OK。The last quiz is going to be next week. Okay, I'm going to upload the question set. Okay, the last question set. Okay, tonight. So you guys will have the quiz next week, and I will also upload the sample final, which is the final that I used last year. OK， 我也会把去年用的这个期末考题，就是上传上去，让你们看一下，大家有个概念，期末考大概长什么样子。OK， 那大概是这个样子。OK，so let's continue our discussion from last week. I'm hoping that we can finish Chapter 5 today, but if not, we should be very close to finishing the Chapter 5. 就是我们如果说今天没有办法把第5章讲完，至少也会很接近。然后我们还有2个礼拜的时间。I estimate that we should be able to finish most part of the Chapter 6, but probably not the whole thing. OK， 那差不多其实比去年的其实已经好一点点。去年的话是第6章，好像只有1堂课半。对 ，OK， so let's get started. OK， 等一下我拿一支笔。这个吗 ？OK。So we talk about the direct sum, okay, of 2 subspaces, okay. So basically, if each vector can be uniquely, represented as the V equal to S1 plus S2, where S1 comes from the first subspace, S2 comes from the second subspace. Then V is direct sum of S1, S2. Okay, and we write V equal to S1, this direct sum S2. Okay, so so this is an example. Okay, the B. Okay, like 101, 110, 100. This is obviously a basis for R3. Okay, because you can see the first vector, it provides like the third element. This is the only vector that provides the third element, and this is the only vector that provides the second element. Okay, so these two are must, and obviously, I mean, you can use this one to adjust the first element. So basically, like this is the very easy to, it's very easy to tell it's a basis. But of course, I mean, if you want to verify it, you can put it in the matrix and check the the determinant of it. Okay, make sure it's non-singular. Okay, so if S1 is span 101, S2 is a span 110, 100. Okay, so then R3 equal to S1 direct sum S2. Okay, this is we know this because because this is a basis for R3, right? So in other words, if this is a basis for R3, or for any dimension, I mean, if you have a basis, it means if V is in R3, V can be written uniquely by alpha 1 V1 plus alpha 2 V2 plus blah 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 plus alpha n Vn, right? This alpha 1, alpha 2, I mean, assuming V1, V2, blah blah blah, Vn, these vectors form a basis for here I'm actually trying to write it in more general form. Okay, say it's Rn, and the V1 to Vn are, I mean, they form the basis for Rn. Okay, then for any vector in this V, vector in this Rn, you can write it, like this. And this alpha 1, alpha 2, blah blah blah, alpha n are unique, right? We proved this earlier, right? Okay, why? Because they are independent. If you have different way to write it, you subtract these two, representation. Some of those vectors in a basis must be dependent, right? So that's an easy proof for, contradiction proof. Okay, but anyway, so if you say if you try to use some part of this basis for a subspace and the other vectors in this basis for another subspace, and then your Rn must be expanded. For example, you have V1, V2, Vk. If you use this to, span. Let's call this one S1, and S2 to be Vk plus 1, Vn. Okay, then we can show that Rn must be S1 direct sum S2. Why? Because any vector, okay, in Rn can be uniquely represented by as this, right? So, you know, I mean, this is up to alpha k vk plus alpha k plus 1 vk plus 1 plus da 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 da. So this part obviously comes from S1. This part obviously comes from S2, right? Right? And this is a unique way to represent this V, right? If there's other way, then we have an issue, as I already mentioned to you guys, okay? Because this Vn, V1 to Vn, they form the basis for Rn. So I mean, if you have other ways to represent this vector V, then that implies some vectors in this basis are dependent, which is impossible, okay? So basically, okay, so if this is the case, according to the definition of like a direct sum, yeah, we have this. Because any vector V in Rn can be uniquely represented by, we call this one as V1, we call this one as a V2. Okay, this V can be uniquely represented by V1 plus V2, where V1 comes from S1, V2 comes from S2. So according to a definition, your V or Rn is direct sum of S1 plus S2. So, because I already showed you the general case, this is obviously a special case, right? In R3, okay, this is like we try to give you like concrete vectors for this basis. So this is must be true. So the other exercise, okay, if V is an n-dimensional dimension vector space, and the V equal to S1 plus S2, prove that dimension S1 plus dimension S2 must be n. Okay, so this pretty much comes directly from what we discussed here. Okay, because if V is an n-dimensional vector space, okay, and V equal to S1 plus S2. Let me erase this. So we know like okay, this is good. We know V is n dimension. So in other words, okay, let me see. Then it's probably easier if I choose to do it this way. Okay, that okay, that the S1 dimension of S1 to be n, dimension of S2 to be k. Okay, I mean, then we know like say there's a basis. Okay. So basis. Then the basis V U okay, and so according to the definition, okay, if V is the direct sum of S1 plus S2, so if that tells us that if V for any V in S, capital V. Okay, so V, there's a unique representation of there's the notation is repeated. So let me write it like a V cap sup 1, sup 2, okay? Because the V1, V2 are already here, okay? So where V1 is in S1, V2 is in S2, right? Right? According to the definition, right? So, but we know like this pretty much tells us that, okay, this what should I say? This basis and this basis together, okay, span this capital V, right? Because any vector from here, okay, because we know this V sub 1 can be written as a linear combination of V1 to Vn, right? And V sub 2 can be written as a linear combination of U1 to UK, right? So in other words, V can be written as a linear combination of this one and this one, right? Right? So from here we know right? Right? Okay. So this is the first thing. We know they span V. Okay. And the second thing, these two are independent. These two bases are independent. Okay. We know the V1 to Vm are independent. U1 to UK are independent, right? Right? No question about that, right? So if they are dependent, what do they mean? So the only thing we need to check, okay, for this m plus k vectors to be, the whole set to be independent is that there's no way that, in between them, they are dependent, right? OK， 就是说你现在你知道他们这些 vector 在里面都已经是独立的嘛，在里面独立，那我们现在唯一要检查是他们是不是 independent， 就是你就看他们两个之间有没有可能那个加起来它不是 dependent， 它不是 independent 啊，对，就是说加起来是那个的问题，所以现在问题是说这个集合上面写的。is 这个 independent， OK。那如果他们是 dependent， for example， 有一些 v 可以被写成 u 的这个假设不失去一般性 ，let's assume like without loss of generality， 可以。Let's assume Vi can be written as like a combination of some, so if they are not independent. Okay, prove a contradiction. If they are not, this one is dependent. Okay, so without loss of generality, okay, assume Vk, no, the k has been used. Vi can be written as like a linear combination of a ui, uj. Okay. Okay, if this is the case, okay, then we will have issue. Why? Because let's just consider Vj, this is a Vi. Okay, Vi obviously is in V, right? Vi is a vector in V, right? Okay, so we know Vi is a vector in V, but we can say Vi, equal to Vi plus 0, where this one comes from S1, this one comes from S2, right? Remember, S1, S2 are both subspaces, so obviously it includes 0, right? Both subspace, all the subspaces include like a 0 vector, right? So this is one way to write it. Another way to write it is 0 plus summation alpha j uj, right? Which this vector is in S2, right? This is in S1, right? So we have two different ways to represent this Vi, right? But it contradicts to the direct sum definition because we should have only one way to represent any vector in this, in the V. So basically, like there's a contradiction. So this this whole set, okay, is not dependent or it is independent. So if this set spans V and they are independent, what does that mean? It means these vectors form a basis of this space, right? So that pretty much means this one plus this one equal to n, right? Like n plus k equal to n. Because n is the dimension of V. Okay? So let's continue, okay? So previously, I mean, in our discussion, okay, we do not care that much about, you know, vectors are orthogonal or not, okay? Orthogonal 就是那个啦，直角啦，对，就是直角 orthogonal subspace. Okay, but now we let's consider, okay, if some vectors are orthogonal, like what does that, you know, what is it going to affect our space? Okay, so for example, the subspace S1 and S2 of Rn are orthogonal if V1 inner product V2 equal to 0 for all V1 in S1 and the V2 in S2. This is definition, okay? So we can define two vectors are orthogonal or not. We can also define, okay, using this definition, okay, two subspaces are orthogonal or not. OK， 如果有任何一个 vector，OK， 在 S1 跟另外一个任何一个 vector 从 S2， 如果他们两个做 inner product 都是等于0，就他们都垂直。OK， 那我们说 these two subspaces are orthogonal。OK， 那 a very simple example I can give you is in R3. OK， if S1 is spanned by E1, E2, and S2 is spanned by E3, then S1 and S2 are orthogonal. Why? Because E1, E2 pretty much means if you consider like a three-dimensional, I mean, because 三维我们还是可以想象的出来的嘛，对不对 ？E1, E2 span 哪一个 space？ 就是那个平面嘛，对不对？过 z 等于0的那个平面，对不对？那你 S2 如果是从 E3 span 出来，那就它基本上就是 z 轴嘛，在 z 轴上任何一个 vector， 那 z 轴上任何一个 vector 跟那个 z 等于0这个平面当然垂直嘛，这没问题。概念上一定是这样子 ，OK？ 当然你也可以 verify，you can verify that too, right? I mean, you know, how, you know, another way to verify it is we just write it out because S1 is spanned by E1, E2. So that means like if V1 is in S1, that means V1 can be written as alpha 1 E1 plus alpha 2 E2, right? Right? So for the similar reason, if V2 is in S2, according to the definition of S2, your V2 must be, well, beta times E3, right? Okay, then you just V1 dot V2. You will be this alpha E1 plus alpha E2, alpha 2 E2 dot beta E3. I think you can do the rest, right? Right? It's very easy, right? Just write it out. I mean, one way you can observe this, intuitively. Another way you can just, just do the computation. Okay. And based on this, we can also define, like if S is a subspace of Rn, then the orthogonal complement of S, okay, is the set S. We say let's just call it S orthogonal. Okay, I don't know because I have no pronunciation for this symbol. Okay, but this represent like orthogonal. Okay, so S orthogonal equal to any U. Okay, any vector in Rn such that this vector dot V is 0 for all vectors, in S. If that's the case, okay, the collection of this U will be S orthogonal. Okay. So this is the definition of the orthogonal complement. Okay. So then our question: if S is a subspace, we need to show that S orthogonal is also a subspace. Do you guys remember how to prove something is a subspace? Do you remember? This is two chapters or 3 chapters. Maybe 2 chapters ago. Okay, 就是两个 chapter 以前的那个 material， 但是因为我们还是在讲那个 subspace all the time， 所以就是如果说你要检查一个 space 是不是一个set 是不是 subspace， 就是说what you need to show is if V is in this set, okay, alpha V has to be in this set too. So this is the first thing. The second thing is if U V in S, U plus V will be in S too. Okay, we need to show these two in order to claim S is a subspace, okay, of something. Of course, that from there we define that addition, of course. Okay, 所以希望大家还记得。那所以 so we need to show that S orthogonal is a subspace. So if a V is in S orthogonal, okay, we need to show alpha V is in S orthogonal too, right? So can we do that? Okay, V is in S. That means what? That means V dot U, okay, where for any U in S, V dot U equal to 0, right? According to the definition of the orthogonal complement, right? If V is in S orthogonal, we have this, right? For any U in S, V dot U is 0, right? This is obviously also true for alpha V, right? Alpha times V dot U, okay, alpha V dot U is also 0, right? Because this one dot U, you just do like a inner product, this one first. This one gives you 0. 0 times alpha is always 0, right? So from here you go here, right? Okay, so the other one, okay, if UV is in S, U plus B has to be, we need to show U plus B also in S. So if, so in other words, okay, if U is in S, UV is in S orthogonal, we need to show U plus V in orthogonal, S orthogonal. So this pretty much from here we get like for any W, okay, in S, okay, U dot W equal to 0, okay, and for any W in S, like a V dot W equal to 0, right? We have this from the definition of like the orthogonal complement. And from here we can get, okay, for any W in S, you know, U plus V dot W equal to UW plus VW equal to 0, right? So we get this, right? So obviously, if S is a subspace, S orthogonal is a subspace too. Okay. Then the next question, okay. Find the orthogonal complement of the column space of the following matrix. Okay. So here, okay, for these column vectors, okay, I mean the column space is formed by column vector. I mean column space is spanned by column vector. So we have two vectors. One is this one, another one is this one, right? Right? Okay. So in other words, okay, your orthogonal complement, okay, any vector in the orthogonal complement, okay, any U, okay, for any U, okay, in this is let's call it like a S. Okay, let's say it's S equal to span. One, two, 1, 0. Zero, 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 1. Okay, the S is spanned by these two column vectors. Okay, and any U in S orthogonal, okay, obviously, you know, U dot, let's call this one as a V1, this one as a V2. U dot V1 equal to U dot V2 has to be 0, right? This is obviously the constraint, right? Then, well, that U small s. Okay, then it tells us that x plus 2y plus z equal to 0. And this lowercase s must be 0, right? Because like this one dot this v2, we only get s, right? So you so for any u in S orthogonal, we have this. The first one, S is 0. And then x plus 2y plus z is 0. So if we let x to be P, Z to be Q, then your Y will be, X to be P, Y to be Q. Okay, Z will be negative P minus 2Q, right? Right? Okay, or if we write it a little bit better, let's separate the term of P and the Q. So it will be P times 1, 0, negative 1, 0, plus Q times 0, 1, negative 2, 0. So it tells us that S, orthogonal is spanned by this vector and this vector. Of course, this notation may not be unique. Okay, you may be able to, write this subspace, many possible basis for this subspace. Okay, this is one of them only. Okay, so far so good, right? Any question? Okay, if no question, okay. Well, it's about like a break. Let's because obviously it will take some time. So let's wait until the break is over, and we will continue the discussion. Okay.好。